So my name is Bolanle Banigbe. I am a public health physician. I've practiced both in Nigeria and in the US, and I am happy to join this lab this afternoon to work with you. Today, we will be going over the lab session on comparing means. In the last two, maybe not the very last two, but in this class, you've learned about comparing means and linear regression. So today we'll just be going over the practicals for comparing means, right? Please let me know if there's something you need me to go over, if you need me to slow down, if you need me to pick up speed, please let me know. Okay, and then please let me know, do you have your RStudio open, and do you have the R Markdown for today's lab? You can just say yes or do a show of hands. Are we ready to go?
Yes.
Yes.
Okay. Okay, thank you. So as anybody, is there anyone who is attending who this is their first lab, who has not attended any of the earlier labs, or who has not had a chance to watch the videos?
Well, I only missed Thursday's class so far. So I've been
Okay. Okay. I asked that question to kind of like judge, or to gauge level of, if you like, comfort with RStudio and R Markdown. So we're just going to go on and start. And similar to what you've done in earlier labs, the first step would be to clear the workspace, right? And the reason that we're clearing our workspace is so that we're sure we don't have anything in our memory that can cause conflict or anything. So here's the command to clear the space. Is rm remove, and we'll just say remove all the lists. List is equal to ls, right? Once we do this, it clears the workspace. There was nothing in my workspace, so that's why there's nothing to clear. And then the next thing we want to do is to set the directory, our working directory, so that R knows exactly where to go look for the things that we want to work with today, maybe like our files and everything. Have you all cleared your workspace?
Yes.
Okay. If there's anything that's, if you need me to slow down, go over something, just let me know. So first, then I'm going to go ahead and set my working directory, right? And one way that you can do this is to go to the lower right part of your window and just go to the settings, copy the directory, copy the clipboard, copy the path to clipboard. That way, you don't have to type out all this long, So this is my working directory. So today we're going to go over t-tests. Is there anyone who would like for us to quickly go over measures of central tendency or talk about mean? Or should we just, go ahead and go into t-tests?
I think we should go into t-tests because we have spoken extensively on measures of central tendency, mean, median, and mode.
Okay, thank you. Thank you, Dr. Chiloka. Okay, so the next thing we're going to do is to import our data, and the first data set we're using is a Heights CSV. I mean, just because it's ith.csv, we know that it's a CSV file. And to import that, we start by calling up our library readr. So I call up my library and say library readr, and then I assign, I create the vector to which I am going to assign my, the name that I'm going to give my file. And because my file path is so long, if I start writing it, I will most likely make a mistake. So I'm just copying it from there. But just go ahead and are we good? Hello? Can you hear me? It appears that things are
Yes,
frozen.
I can hear you.
Oh, okay. Okay. So is everyone, like ready to run? Have we imported it? Actually, my environment is not.
Yes, we are good.
Loading. Okay, yeah, I see that you're good. I also see that my environment is not loading, so I am wondering why. I think I made a change. Hold on 1 minute. I'm going to stop sharing for a minute. I'm actually just going to reload my R, reload the environment. Let's see, give me a minute, please. Okay, great. Okay, great. Sorry about that. My RStudio was hanging. Okay, so like the steps that you followed in the earlier labs, once you get a new data set, it's just good practice to look at your data set and see, okay, what's in here? Let's get an idea of what I am dealing with. And one way to do that is just to look at use the head function, right? When you use the add function, it shows you the first few rows and all the columns in your data. So for instance, this is just showing us the first 6 rows. And we can see that this, of course, it's showing us the first 6 rows. There are more rows than that in the data frame, but it's showing us that we have 6 columns, and we can see that, the IDs, the ith2, and then ith100. Another thing that we can do is to also just look at the median, just to give us an idea of, what's the median of this data. And so here we are. I've just run the R code chunk, and you can see that the median is 100. So would anybody want to give it a shot to show us how they would obtain the proportions? Anybody? If you want to, if you just let me know, then I would I would allow you to share your screen, or better still, just. Anybody want to give it a shot to obtain proportions?
Let me try.
Okay. You can share your screen. I'm going to stop sharing my screen so that you can share your screen. You have an error message. Do you know why you have that error message?
I don't know.
Okay, does anybody want to, like help him? Anybody? Why do you think he got this error message?
Right.
Okay. Anybody has an idea why Dr. Chiluka got the error message? Okay, so the reason why you got the error message is because you're asking R you want the proportions of the table called height table, right?
Yeah.
So you said I do prop dot table of height table, but it's telling you object height underscore table not found because it's not specified.
Okay.
So I don't know if this was, like an error in the code, or if the person that wrote this code actually wanted to see if we're following what we're doing. But first, we need to specify height underscore table, that object. We need to specify that object before we can get the proportion of that object, right? So do you want to take a shot at specifying height.table? What would it be?
Height.table.
So basically, we're trying to say we want to generate a frequency table, right? That's what we want to do at this step. And we have told R, there's an object called height underscore table. I want you to convert it into a table of proportions. And it is telling us, I don't know, you've not specified height underscore table. So maybe we should just take the proportions, the frequency of height underscore table, let's take the frequency of that variable called height.
So how am I going to go about it?
Okay, so let me share my screen. Do you want to stop sharing your screen?
Okay.
I'll share my screen and then we can do it together. I don't know if they just wanted to test whether we're following, but here we are. Same thing I have on my in my code, proportion of height underscore table, except that there's nothing called height underscore table. So can you see my screen?
Yes.
Okay, so the first thing I'm going to do is say, okay, I am going to specify height underscore table and call it the table of HT, which is the name of the data set we're using, $height. So now I have specified this object called height underscore table. And in that object, I am storing a table of height. Does it make sense?
Yeah.
Does it make sense?
Yes. Yes.
Yes.
Okay,
Yes.
so let's now see what is inside height underscore table. Can you see it? So it's basically done a frequency table of all the different values of height in that data set. Please let me know if you're following, if I should go over it, if I should move forward. So basically it's saying that, let's assume that the height is in centimeters, for instance. It is saying that this variable, the column called height in that data set, there's one entry or one occurrence of 80, one occurrence of 83, two occurrences of 85, 100, the height 100 centimeters came up 7 times, you know? Does it make sense?
Yes.
This is a small group, so, you know, like, let's just jump in. Okay, so now that we have specified this object called height underscore table, we can go ahead and run this again. So if we now say, okay, you've given me a frequency table. Now I want to see the proportions. I can now say prop the table of height underscore table. So now it can see it, right? Can you see that now it has converted it into like proportions? What proportion of the entries are 89? What proportion of the entries are 100? Can you see?
Yes.
But this is really just, you know, this is difficult to look at. Like 0.02, for instance, if you're looking at what proportion of the entries are 87, 0.020833. Nobody works with all these long decimal places. So then we can use the round command to round down the number of decimal places. And for this one, can somebody, if you look at line 61, can somebody tell me what line 61, when we run line 61, what will happen?
I think it will multiply the proportion value by 100.
Exactly. Then what else will it do?
This digit equals 0. I think maybe it should just be a single number.
Absolutely. Absolutely. So what is going to happen, like you correctly said, is it is going to multiply, and we can see the 100 times prop the table. So it's going to multiply each of these numbers by 100 to just make it less annoying and so many trillion decimal places. And then because we specified digit equals 0, there will be no decimal place, so 0 decimal places. What it means then is that if we want 1 decimal place or 2 decimal places, we can specify the number of decimal places we want with this digit dots, a digit equal to something, right? So let's do that and see. I'm just going to say round it, multiply by 100. Oops. Multiply by 100, prop the table, height underscore table. And generally, I like to take R suggestions because, so as I'm typing, sometimes it just suggests things. I like to take the suggestions because R can be very sensitive to things like spaces, like uppercase or lowercase. I've run into trouble many times because I put an uppercase letter in a place where there was not supposed to be uppercase, and then I'm spending the next 5 minutes trying to figure out why my code is not working. So if R suggests something, then I take that spelling. So if we do this, then you can see that it has now not just multiplied by 100, it has also given us this percentages that are just, that have no decimal places. And this looks easier than what we had before, right? Have you all been able to do this?
Yes.
Okay, great. And you know, like I said earlier, we can have one decimal place also. So I'm just gonna do that and say digit equal 1. If I say digit equal 1, now you can see that there's one decimal place. And if you want 2 decimal places, that's also okay. So we've now learned how to create a frequency table, multiply by 100. You can get a mean, you can get the median of your data. You can look at the first 6 or first 10 observations in your data set, just to get an idea of what is in this data, what's going on here, right? But sometimes you want to do more than, you don't want to really be doing this thing row by row. You want a command that will give you more than one output at the same time. And that is where table 1 comes in, the table 1 package, right? So the table 1 package, it can give you all the baseline variables. You can just, so if you create a if you specify a variable, maybe the height, or maybe in other data sets, the age, whatever, it can just tell you a lot of information about that particular variable in one set of code, rather than you writing one line, mean, another line, median, another line, standard deviation, another line, minimum. Does it make sense? Does this make sense, what I'm saying?
Yes.
Okay, so we're going to use the table 1 package. Have you used the table 1 package before? If you haven't used the table 1 package before, if you haven't used any package before, the first thing we want to do is install the packages. Please don't put the £. I put this because I don't want R to run it. I already have it installed. So if you don't have it installed, then you want to do install the packages table 1. Then R will install it on your computer. And then if you already have it installed, then of course we call it up using the library function, library table 1. So that's what I'm going to do since I already have it installed. So please let me know if you have been able to call up table 1 in your library. Is anybody having a bit of trouble calling up table 1?
No, I've done that.
Okay, great. So is it okay to move forward then?
Yes.
Okay, great. So now what we're going to do is instead of going through each of those variables one by one, you can actually ask R using table 1 package to give you the summary measures for more than one variable at a time. So here I am going to specify the variables that I want to look at. And I'm telling it I want to look at, because it's more than one variable, I'm using the combine, the C for combine. And I'm saying, I want to look at the variable called height. I also want to look at the variable called height 2 at the same time. Then I am going to say, the name of my table is table 1 or tab 1. And I am going to call up this command, create table 1. Like I said, I usually like to take our suggestions. Create table 1 So the arguments for this command, you have to tell it. You have to tell R, which variables are we using? So the variables that I want R to bring up, I already specified them. Their name is VAS, right? How are they separated? What separates them is just comma, because this is CSV, is a comma separated file. What is the name of the data frame that I am using? Is HT. I was the one that specified that earlier. And then R is asking me, should I include NAs in the analysis? And I'm saying, no, don't. So include NA is equal to false. I don't want NAs. And then I'm asking R to then give me a summary of tab 1 that I just set up. Are these steps, are they easy to follow? Are you able to follow them? Okay.
Yes.
Okay. Oops. I don't know what I did. Okay, so here is what we see. So now you can see here the two variables that we asked R to look at, height and height 2. And it is telling me, it's giving me a lot of information, a lot more information at one go about these two variables. So it's N, the number of observations, so there are 96 observations. The number that I'm missing, 0. None of those observations are missing height, or height 2. The percentage missing, of course, is 0. It's telling me the mean. So the mean of height, or the mean of the variable height is 9. It's telling me the standard deviation, the median, the 25th percentile, the 75th percentile, the minimum value, the maximum value, the skewness in this variable, the kurtosis of this variable. So you can see that this one gives us a lot more information about a particular variable at once. Each of these things, you can write a line of code for R to tell you, or you can just use this table, create table 1 that tells you everything at once. So I'm going to pause here and just take questions.
Thank you. Please, is it the same thing if I say summary of HT?
If you do summary, why don't we try it out? It's not exactly the same thing. It will give us slightly different data. So why don't we try it out? Can you see what summary of HT gives us now? Have you tried it out, Dr. Chiloka?
Yes, yes.
Okay, so where is the difference?
I think in the percentile, 25th and 75th percentiles.
No, I will, what's it called? I will beg to disagree. So for instance, if you look at height, here it says height P25 to 25th percentile is the same thing as a first quintile, right? So for height is the same thing. But so the numbers or the results are going to be the same, but this gives you different statistic. Here it tells you the minimum, the first quintile, which is the same thing as the 25th percentile, the median, it tells you the mean, tells you the third quintile, which is the same thing, the third quartile, which is the same thing as the 75th percentile. However, table 1 also tells you the number that are missing, right? The percentage is missing. Summary doesn't tell you that. Table 1, the table 1 command tells you the skewness and the kurtosis. So just it just basically, skewness and kurtosis are just measures of, like the symmetry of your data. So if you use summary HT, it gives you similar information, but table 1, the table 1 command gives you a lot more information. That would
I'm looking at it that even the mean using the mean and the median, one can get information of the symmetry. 2.
Oh, absolutely. You can get information on the symmetry because if you come like you're like, okay, so tell me, how would you go about that?
Like when the median is tilted more to the left of the mean, then we can say it's more of left skewed. And if it is tilted to the right of the mean, then it's more of right skewed.
Yes, you're correct. However, you know, like I think I've concluded that there are 2 categories of people when it comes to statistics. Some people are more artsy. They can imagine it. Some people like me, we want to see the numbers. So I agree with you that, you know, like your explanation is correct. But I usually ask, how skewed? Is it skewness that I should be worried about? Or is this skewness? Because really, in real life data, it's difficult to get that normally distributed, you know, like Gaussian curve. It doesn't really, most of the time is an approximation, right? So I usually ask, should I be worried? Is it slightly skewed, heavily skewed, terribly skewed? Can I use my test? Can I use a statistical test based on the skewness? So I guess that's why maybe for people like me that like to see a number, that's where skewness and kurtosis comes in. And some people are just really more intuitive about it. I admire it, but I don't think that's the kind of person I am. So basically, I am saying that you're correct. You can look at the mean and the median and say, does this look symmetrical? And you can also just say, I want hard numbers. Let's calculate the skewness and the kurtosis of the data. I hope I didn't confuse anyone.
No.
Hello? Do
we
we
are
still
following.
have? Okay. Ozioma, are you following?
I think I am.
Okay. Okay. Please just, you know, let me know if there's a need to slow down, if there's a need to go over something. Okay, great. So we're just going to go back. We're just going to go on. And here, I think Dr. Cheluka was just preempting some of the conversation. Here, you can also specify that maybe one of the variables is not normally distributed. So you can say, for instance, it's not normal. Non-normal just means, you know, it doesn't approximate the normal distribution. And if you tell R, or if you tell the package that it is not normally distributed, then it will give you the median and IQR, interquartile range, instead of the mean and standard deviation. Can we try that? Let's just see what it will give us if we specify that height 2 is not normally distributed. If we tell R that, look, this tab one that I just specified, height 2 is not normally distributed. Let's see, can we all try it and see what will come up? Oops. Did anybody get an error message like I did?
No.
Okay, great. I have 2 equal signs. That's why I got that error message. Oh. Okay, so you can see now that for height 2, instead of giving us the mean and standard deviation, it's giving us the median and interquartile range, right? So basically, when you're using table 1, you're not just forced to get the mean and standard deviation. For your variables, you can also get the median and IQR if that is more appropriate. Does it make sense?
Yes.
can we move on to look at histograms?
Yes, we can.
Okay. So basically, histogram, you can get an histogram using the Bezier command called hist. Does anybody want to share their screen and just show me how they would do an histogram? Oh, we have a few more people join us. Welcome. Anybody wants to volunteer to? Okay. So which variable are we using?
The height, HG.
Great, great. Okay, great. What can somebody tell me what they think about this histogram? Like, what do you not like about it?
It's just monotonous.
What do you mean monotonous?
Everything in one color.
Yeah, everything in one color, yeah. Any other thing, any other observations?
It's not like if you have to plot an epic curve, it's not starting directly from 1, 0, 1. It started right from 80.
Because that's like the minimum value. Yeah, so you're right. And then another thing that I just don't like about this Bezier is that what kind of title is this? Histogram of HT dollar height. So the Bezier, you can stop sharing your screen now. The Bezier, I mean, you can specify. It's possible to specify. It's possible to specify the title, to specify the axis label and all of that. But a better package to use for customizing our graphs and everything is the ggplot. As anybody, did you use the ggplot in earlier sessions?
Yes, we were introduced. It was introduced, and some of us were able to install.
Okay, great. So if anybody does not have the ggplot yet, so we will do the same thing. Library, sorry, no, not that. Install.packages. Let's do install.packages, ggplot. So if you don't have ggplot, if you've not used ggplot before, and you don't have it in your RStudio, please do install.packages. But if you have ggplot already installed, like I do, I am just going to call it up from my library. Huh. Interesting. Okay, I'm going to call it up from my library and just say ggplot2. So do we all have ggplot called up in our library? If you look at this, note in your R Markdown, it already specifies for you the format, the general format in which you use for ggplot. And it's basically like first you call the ggplot command, you specify the name of your data set, and then you start adding aesthetics to it. And the first aesthetic that you just add is like, what's your x-axis? What's your y-axis? If you have a y-axis, and sometimes you can even have a z-axis. So, you just tell it, the first thing you do is to specify your axis. Then you start adding other aesthetics, the colors, the kind of lines, the labels, everything. So if we just look at this example here, for me, it's line 106, sorry, 107. So we're specifying, we're naming our plot P, and you call up ggplot and you say the name of my data here. So the name of my data frame is HT, and then my x-axis, what I want you to plot on my x-axis is the height. Then I take the P and I say, this P that I specified here, and then I start specifying other arguments. The fill, I want it to be black. So that's the color of the bars in my histogram. The alpha is 0.25. This alpha is like is a measure of the transparency. How dark or how light do you want your black to look like? And then the bin width. If you remember the histogram, let me just run it again. Here, if you look at this one, for instance, the bin width is 5. So it's just, this is 80 to 85, 85 to 90, 90 to 95, 95 to 100. The intervals are very wide. So you can specify the intervals that you want. You can say, I don't want the intervals to be that wide. I want the intervals to be a bit, I want the intervals to be a bit narrower. So basically that's what you're doing here with the bin width. And then labs is labels. So now you can say, this is what I want you to call my y-axis. This is what I want you to call my x-axis. So you basically are able to specify what you want more than just the histogram. So can we do this? Please do it and let me know if it works for you or if. Amatoye, how's it going?
Yeah, it's going on well. Actually, like I'm in transit, and so my laptop.
Oh, okay. Okay, that's all.
Once I get home, I'll watch the video and just.
Okay, that's fine.
Thank you.
Uchechukwu, how is it going? Have you been able to run your? Does everybody have something that look like this?
Yes.
Okay, great. I'm also going to pause now and take questions. Do we have any questions?
Excuse me, please. I want to, how do I specify the argument? Because I have my own personal data where I had for actually Lassa fever outbreak.
Do you want to share? Do you have it now, or do you want to share your screen? Like
yes,
if you have it.
Yes. I have the one for monkey pose.
Okay, so what argument are you trying to specify?
Like in a year, like in an epi year, we started having outbreak around September. When I plotted the epi curve, it started from where I started having a value, like 4, 5, 6. The zeros were ignored. So I didn't know how to specify to start from 0 to show the 0, the month without outbreak as before the outbreak.
Okay, so I'm putting it in the chat. So you can use xlim, okay, and then you specify, the name of the month. So basically the x limit, the x-axis limit. Okay. Since we all don't have that data, so that we can move on. Or basically you can specify the limit. Does it make sense?
So X limit will now start from
whatever month it is.
Month. Okay.
Like, you said your epi year starts from September, right?
September, yes.
Yeah, so you want to do X lim is September or Sept or what, however it is in your data.
Okay, okay. Thank
Okay, you're welcome. Okay, so let's go on now and talk about box plots. So we want to do box plot. If you're using exactly the same R markdown scripts that I'm using, then you don't have this line, right? Can you see my screen?
Yes.
So basically, before we can do the box plot, you have to import the resident doctor's data set into your R environment. So can you all import your resident doctors.csv file? Remember, you have to use the read_csv and then you specify the path. Please let me know when you have read it into your data set or into your, so we call it RDS. Then you specify the path. I'm just going to do that. Is there anyone who has not read it in yet? Anyone with their computer who has not been able to read it in? So should I assume that we all have it?
Yes.
Okay, great. So now we're going to make a box plot. Does anybody want to volunteer to do the box plot using this code here? So it's basically the command is the box plot, and then you specify your data, the name of your data frame. This time around it's RDS. Then you specify the column that you're looking at. So RDS $age. And then here ylab equal age, comma years. So basically ylab is the Y label. The name of the Y axis will be age in years. And then the xlab equal all. So the name of the label of the xlab, of the X axis is all. Does anybody want to show us what they've done? I'm going to stop sharing.
Okay, box plot.
Sorry, say that again.
Oh, let me-
Error X limit is X limit. Okay, so can you look in your data set? Is it, you can just use a view, capital V, view, yeah, then RDS in parentheses.
Bracket.
Yes. No, you don't need you don't need columns around it, just RDS. No, you need you need the bracket, not the colons. RDS. Okay. So you can see that your variable name is in lowercase. Can you see? Age. Age is in lowercase, but for your box plot code, you wrote it in uppercase. So can we redo the box plot exactly with lowercase age? You might be missing the open bracket. For some reason, I can't see the code you're writing. If you want to like scroll up a little, just scroll up a little.
Okay, I might need
Okay,
to
fantastic.
clear.
Yeah, fantastic.
I might need to clear.
So your apostrophe should be around the close. You should close the apostrophe after years. Exactly, and then you should close the apostrophe after all. Yeah, so now we have a box plot. Is everybody else able to get a box plot?
Yes. Oh,
Okay, so okay, great. So thank you. I will share my screen and then we can move on. So now we're done with the visualization. We're going to go on and talk about the t-test. And from class, remember you talked about one sample t-test when you're comparing the mean in a sample to a pre-specified mean. And then there's a two sample t-test, which can be the paired t-test or the independent t-test, right? So the first example here, and we already have the formula for using the t.test command in R, is t.test, and in the bracket we have the x, our x variable, our y variable, and then we say the y variable will be null, and then we say the mu, the difference is 0, because our null hypothesis is that there's no difference between the sample in our mean, and the mean in our sample and the pre-specified mean, right? So here's an example. Dr. Samuel from Koso Town believes citizens in his town consume calories differently during Eid than on regular days. So he wants to test his assumption using a one sample t-test. He's gotten information that the mean calorie consumption on regular days is 2,100 calories. And the mean calories from a sample of 100 people on Eid is 1,850 calories with a standard deviation of 300 calories. Sometimes you have a data set, like maybe with all these 100 people, one observation per row, and then you're able to say, this is my data set. And sometimes, like in this case, we don't have a data set. We just know that the mean calorie among these 100 people is 1,850 and the standard deviation is 300. So when you don't have when you don't have a data set, what you have to do is to almost like simulate what the data set will look like. and we're assuming that it is from a normal distribution. So we create this object called id. Our norm just generally means we're simulating, assuming that it is normally distributed. This is the number of people in the sample, the 100 people. This is the mean of that sample, and this is a standard deviation of that sample. I can see that in the narrative, it says 300, in the code, it says 200. I would just leave it so that we don't mess things up. I suspect that someone made a mistake. So, but the principle is still the same. So we're going to create almost like a simulated data set of these 100 people, because we don't have the information on 100 observations. We only have the sample, the summary measures, right? So once you create this, simulated data set of 100 people, then you can compare that with the 2,100 calories average that people eat on a good day, and decide if there's a difference between mean calorie consumption on regular days and mean calorie consumption during Eid. Does it make sense? That's the theory of it. Does it make sense?
Yes.
Yes, it does.
Okay, great. So since it makes sense, please, Ozioma, Omotoye, Mahmuda, if there's something that you need me to go over, just raise your hand, just say something, right? So let's generate, or let's create our simulated data set. And basically we're just going to say the name is Eid, and then we say normal, can you simulate a normal distribution that has 100 people? The mean is 1,850, and the SD is 200. So I tell R to create that, and it does. Now I will go ahead and just test if there's a difference between this calorie consumption during the Eid and calorie consumption during regular day. And I'm now doing a one sample t-test, right? Because I only have one sample. So I'm doing t.test. And I say Eid. That's remember what we assigned Eid as this, the parameters from the sample that was collected. And then mu is 2,100, which is what happens on a regular day. Are we all at this point? Please let me know when you get to this point.
I'm following.
Yeah, following.
Okay, great. So then once we do that, this is our result. I'm going to give you 1 minute to look at the result of this one sample t-test and tell me what you think. What your conclusion is. Any takers? What's your conclusion about this one sample t-test?
Yeah, I have a question. Why do I have a different T value? And I guess the mean is also different for me.
What's your T value?
Minus 10.715.
Okay, so let's go back and see, do we have the same?
Yes.
So the thing also that you have to realize is that because this Eid, right? This one, do you understand? Can you see the one I'm highlighting?
Yes, I can see it.
Yeah, we're just asking R to simulate. So every time it simulates, it comes up with slightly different numbers. Our conclusions should be the same, but not necessarily the exact numbers, because it's just like randomly generating 100 values whose mean is 1,850 and whose standard deviation is 200. Every time it randomly generates that, there will be slight differences. Does it make sense?
Yes, it does.
But would you, the conclusion that you have, do you want to share your screen? I want to see. What I will be very worried about is if our p-values are so different, if our 95% confidence interval are just, like way off, and we cannot arrive at the same conclusion. Are you able to share your screen where you are?
Yes, I can.
Okay.
This is what I have.
Yes. So, like I said, I am not surprised that our sample mean, our t statistics are slightly different, because we're basically asking R to simulate these numbers. It's a simulation, but our p-values are not different. I am going to look at, just exiting full screen to look at my own 95% confidence interval is 1,807 to 1,893. Let me see what yours is. 1,000. Okay, that's huge. However, our conclusions are not different, right?
Yeah,
Right?
yeah.
Okay, so the reason that we have these different values is because our EAD is a simulated data set. It means that you and I are not using exactly the same thing. R is not using, your version of R on your computer right now is not doing exactly the same numbers as the version of R on my computer. However, the mean is the same, the standard deviation is the same. So when we compare that sample to a sample to another sample with mean 2,100, the conclusions will be the same. Does it make sense?
Yes, it does.
Okay, thank you. If you'd stop sharing your screen, then we can move on. Okay. I will share my screen. Okay, so we conclude that because our p-value, oops, why did I do that? Okay, so because our p-value is very small, because the mean of 1,850 falls within this 95% confidence interval, we reject the null hypothesis that there's no difference between calorie consumption on regular days and calorie consumption on EAD. Are we on the same page?
Yes.
Yes.
Okay. Okay, so do you agree with my reasons for rejecting the null hypothesis, or do you understand my reasons for rejecting the null hypothesis?
Yes.
Yes.
Okay, great. Okay, so now we're going to practice. And here it says that you have a
Sorry.
new CMD at the Lagos Hospital. Hello?
Yeah, sir, please. I actually don't understand the reason why we rejected the null hypothesis, please.
Okay, great. Thank you for your question. So our null hypothesis is an hypothesis of no difference, right?
Yes.
So basically we're saying that the mean calories consumed during the EAD is not statistically different from the mean calories consumed on a regular day. To test that hypothesis and see if our hypothesis is correct, if we should if our hypothesis is correct, then we collected this data from 100 people on EAD. Their mean calorie consumption was 1,850. The standard deviation was 300. Then we know from maybe existing data or something that on a regular day that's not EAD, the mean calorie consumption is 2,100. So since we don't have a data set, with 100 observations, we ask R to simulate what that data set would look like. And so we specify, we tell R, look, this is our data set, it's called EAD. It's normally distributed, 100 people in the population. The mean is 1,850. The standard deviation is 200. Then R does that. Then we now say, look, we want to do a t-test, a one sample t-test, where we compare the EAD, calorie during the EAD to calorie on regular days. And this is our result. Our t-statistic is negative 11.48. Degree of freedom is 900. Degree of freedom is n-1 in this test. And we say, look, the mean is 1,850.719, right? And then we say, what are the chances? We have a 95% confidence that the true mean in the population falls within this range, 1,807.6 to 1,893.7. That is our 95% confidence interval. If our mean falls within that range, then we say, okay, it's a mean from this population. And then our p-value. So our p-value is, this is a scientific figure. This is a scientific number. It's 0. Many zeros, 0.0000. In this case, you just say less than 0.01. So our p-value, the probability that we will find a mean of this level, or a mean that's at this level, if the null hypothesis was true, is really very low. In that case, we reject that, we reject the null hypothesis and say that this value is too extreme to be due to chance if our null hypothesis was true.
Oh, okay. Thank you for the explicit explanation.
Okay.
Yeah,
I hope I
okay.
didn't confuse anybody. Okay. Now let's go on and do a practice. So in this case, we're also going to practice using the one sample t-test. You're the new CMD at the Lagos hospital, and you asked all the 187 residents. So this is the total number in our population, 187. You asked them how many hours they worked last week, and you calculated a mean. You obtained a mean of 71.6 hours and a standard deviation of 16.9 hours. You want to determine whether the calculated mean of 71.6 hours is significantly different from 40 hours, the typical number of hours for a work week in the general population, right? Remember, in this case, we also don't have a data set. We don't have a data set that has 187 observations for this population. We only have the mean and the standard deviation from the population. So does anybody want to take a shot at how they would calculate the one sample t-test here to determine if the number of hours worked is different from the 40 hours in the general population?
Yes, I've done mine, so I don't know. Unless you want to.
Okay, so let's give 1 more minute. Is there anyone who's not sure how to go about it?
I'm not sure. I don't think I'm
Okay,
sure.
Mahmuda.
I'm sure.
So basically, let's come back to this example. Remember, in this example also, we didn't have a data set. We only had the mean, the standard deviation, and the number of people that were surveyed, right? And what we did was, the first step was we asked R to simulate what this data set would look like.
Yeah.
And once once we had that simulation or that simulated data set, we brought it into this test, the t.test, right? And so that's exactly what we're going to do here. So let's assume that let's assume that the object is called hours. I'll just say, can you simulate for me a data set with 187 people with a mean of 71.6, right? Those are the information that we got from the case, and then a standard deviation of 16.9. Does it make sense up to this point?
Yes.
Okay, so we simulate that. R holds onto that. Then I say, I also know that in the general population, the regular working hours is 40. So I want to see if my population of resident doctors, if they work more hours than the other people. So I'll say t.test. Then I'll bring in my simulated data set that I named hours. Then I will say mu, the mean in the general population is 40. So I'm asking R, can you find out? Can you tell me if ours is significantly different from the mu, which is the mean in the general population, right? And then R tells me that it has done a one sample t-test. You can see the name of the test. And I just like to check this, what R has done. Because sometimes I'm thinking something, but I'm too tired, I'm typing something else. I want to know. I see the test that R says it has performed. And here you can see that the T is 26.32 hours. The T statistic is 26.32. The degree of freedom is 186. And it says here, the mean in this simulated sample, we have to remember that this is a simulation. So if you do it every time, the values will be slightly different, but the conclusions should not be different. So the mean here is 69.9. It tells me the 95% confidence interval is 67.1 to 72.2. Does my mean fall within this range?
Yes, the mean is within the range.
Absolutely.
Within the confidence interval.
So that's one thing you're looking for, right? So I want to see, is this a mean actually, can I confidently say that this mean came from this sample? The answer is yes, right? And then the p-value is less than 0.001. So what do you conclude?
Significant.
Significant what?
We reject the null hypothesis that states that the mean working hours and the reference and the compared mean and the reference mean are equal.
Absolutely. So if you were writing this, if this was your paper or this was your report, you would then say that the mean number of hours that these resident doctors worked is significantly higher than the mean number, that people in the general population, mean number of hours people in the general population worked. Does it make sense?
Yeah.
Yes.
Yes.
Okay. Is it okay if I move forward?
Yeah.
Okay.
Yes.
Thank you. So now talking about the paired t-test. The paired t-test is when you collect data about the same person or the same people at different times. So before and after. What is the, what happened? What's the status now? Then we do something, we take something away, we add something, and then we measure the status, the same status again at another time. And we say, is there any difference? Did our intervention have any effect, right? And you have to really understand the way that the data was collected so that you can, if you see two different groups, you want to understand the way the data was collected. That's what tells you whether it is a paired t-test or it is an independent t-test, because you really have to be sure that you're using the right type of test. So here, let's go back to our example of the new CMD. So the new CMD found that, as a matter of fact, these residents were working more hours, significantly more than people in the general population. So they employ more doctors, or they do one or two things. And then after 8 weeks, after 12 weeks, they want to know if what they did, their hiring practices, made a difference. Did it change the number of working hours? Because sometimes you implement an intervention, it doesn't work, right? So they want to know if their hiring practices, whatever the things they did, whether it changed the number of the working hours for the residents. So they call the same people again and say, in the last week, after 12 weeks of intervention, say in the last week, can you tell me how many hours you worked? And they found out now that after 12 weeks, the mean number of hours worked was 63.8 hours, and the standard deviation was 17.3. So now we want to know if hiring practices made a change. But because it is the same individuals that you collected data on before and after, you will say that their observations are paired, right? Does it make sense how it is paired?
Yes, it does.
Okay, great, thank you. So now you want to conduct a paired t-test to test the null hypothesis of no difference. So your null hypothesis is there's no difference in the number of hours worked before and after the intervention. And your alternative hypothesis is that there's a difference. Here you don't have a data set. So we're going to simulate the same way that we simulated earlier, except that now we have two different time points, right? Can you see this? So we call the first data collection week 0. We're asking R to simulate a normally distributed population that contains 187 people, that has a mean of 71.6 and a standard deviation of 16.9. That's the pre-data. Then at week 12, we're asking R again, can you simulate a normal distribution that has 187 people with a mean of 63.6? That's the new information that you collected, and a standard deviation of 17.3. Here it says 16.9. I changed it just to be true to the case. Okay, so now I'm asking R, can you simulate this? And R simulates it. So now we have simulated, data for the 2 different weeks, right? For the 2 different time points. And I want to do a paired t-test. And they've already given us the general formula. Your t.test, you specify your X, your first set of data, Y, your second set of data, and you tell R paired is equal to true. And this alternative is equal to 2.sided. It's a 2-sided test. You're interested in whether this difference is significantly less or the difference is significantly more. Do you understand? Because in some instances, your results can go either way. Your intervention can make things better or actually make things worse. So here you're telling R, I'm interested in both sides. Have I confused anybody yet?
No.
Okay, thank God. Okay, so now we're just going to run the test. This is the code, and our X is week 0, our Y is week 12. We're going to tell R paired is equal to true, and it is 2-sided test. And here is what we have. R tells us, I actually ran a paired t-test, which is what we wanted it to do. Can somebody tell me what they see? Or how would you interpret your result? If you were writing this up, what would you say?
there is a significant difference in the working hour, and it falls within the range. The mean difference is 5.36, which means by the second week, the doctors worked 5.3 hours more.
Or less.
Do they work more or do they work less? Remember, you're subtracting week 0 from you're subtracting week 12 from week 0. So they worked, you're right, they worked 5.36 hours less. And the 95% confidence interval of the mean difference is 1.8 to 8.9 hours. So the true mean difference certainly falls in this range. And our p-value is 0.032. So we can say that here we will reject the null hypothesis of no difference, right?
Yes.
Does it make sense?
Yes.
Okay.
Yes, it does.
Okay, thank you. Can I move on?
Excuse me, but what happened when we have the mean difference to be negative, maybe negative 5.36?
Because of the way that we set up who's the X and who is the Y, we're basically saying that, you know, the X where we started from is week 0, right? The Y where we ended up is week 12. So it's like week 0, the number of hours they worked before minus the number of hours they worked after. It is, the difference is positive, meaning that they worked longer hours before than after, right? If we had switched this and said t.test week 12, week 0, it would have been exactly the same number, except that it would be negative. So we're saying that compared to now, the hours they worked before was higher. Do you understand? So if we switch it, the mean difference will be negative. The 95% confidence intervals will be negative, but the conclusions will be exactly the same. It depends on, that's why you have to understand what you set into your code.
Okay.
Okay, thank you. Thank you for that question. Okay, so here is, something really fancy that you can do. We can actually convert this, like week 0 and week 12. This simulated data, we can convert them to data frames, right? And use a different approach. So basically it's saying there's more than one way to run this t-test. We still don't have the data set that they collected from the field, but we can convert our simulated data sets into data frames. And this is what we do. We just use the as.data.frame command. And we call it, remember where we got week 0 from, right? We asked R to run this simulated data set. Does everybody still understand where we got week 0 from?
Yes.
Okay, so we can convert that week 0 into a data frame. You just use as.data.frame. And then you assign a variable. You say week 0, I want you to turn it into a numeric variable. And then you can rename it. How do you rename? You call up the library, you call up the data.table, and then this is like this is the format. You use the command called set names. df, that's the name of the data frame. Remember, we just assigned it week 0 here. The old name is week 0, and then we want to change it from week 0 to hours. Can you try it and let's see if there are questions or if there are challenges? So while you're at it, I haven't run any of this code chunk. So this week 0 that you see here is the week 0 that we specified above, right? So if I view this with 0, this is what it looks like. This is a simulated data set. But it is all character. So I want to, that's why we're converting it to numeric here. And you can see that it doesn't really, there's no variable name. It's just values. And that's why we specified a variable name called week, and we turned it into numeric. So please run it and let me see if you have any questions. Does anybody want to share their screen and show us what they're doing? Any progress? Can someone tell me where they are now? Hello, everyone. Hello, is there something you would like me to go over?
I think I'll stick with the former method.
What have you done so far? Why did you decide that you would stick with the former method? Anybody else? Mahmuda?
I'm actually confused. I don't know. I'm trying to get it right.
Okay, tell me, where are you confused?
Okay, I think I'm trying to correct my mistake.
Do you want to
Trying
share your
get it right.
screen? Is that possible? So that we all look at it. I can stop sharing.
Mhm. Trying to assign.
I can't see your screen yet. Can anybody see Mahmuda's screen?
Okay, so this is the
Okay,
network.
great.
It's really.
Okay, great.
Oh, okay. So.
Okay, so where is the challenge?
Just want to try it again. I don't know.
Sorry?
And I just want to try it again. I don't know where I got it wrong. And the enter it as this line 222 as numeric then
222, yeah? So you've already assigned the you created the object week 0 as a data frame.
Yes.
I can see that. Then you assigned you created the variable week inside week 0, and you said you wanted it to be numeric, yeah? And then you wanted to change the names. I can see set names, week 0, then hours. Error in set names, items of old, not found in column names, week 0.
I have to enter the library command first.
Oh, okay, you didn't call up the library. Is any other person having challenges with this? Go on, Mahmuda, and call up the library. Let us see.
Okay, 0 then. Here from the data file.
Sorry?
Probably out.
Your voice is breaking.
Can you hear me?
No. I lost you. We lost your audio for like a few seconds.
Yeah, sorry, that was my phone.
Okay, so should we move on? And then if we have more time at the end, come back to this.
Okay. Yeah, it's fine. Okay.
Or you can type your question into the chat because your audio is breaking, so I'm not able to follow what the challenge is. Okay, so basically remember that we're just trying to think about, or we're trying to walk through a second way of doing the t-test, the two-sample t-test, sorry, the paired t-test, which we already did earlier. And so the week 0, which is the simulated data set that simulated data that R created for us, we converted it to a data frame. And we're going to do the same for week 12. This is the week 12 simulated data set, and we're asking R to convert it to a data frame as .data.frame. And then we create a variable called week in the data frame called week 12, and we say it is as numeric. So we convert it to a numeric variable, and then we change the name from week 12 to hours. So here we are, and that's what we've done. And now we want to merge the two data sets, two data frames, week 0 and week 12. Has anybody used the dplyr library before? dplyr. Has anybody used the dplyr library before? Please let me know.
No.
Okay. If you have not used it before, then you have to go to do install.packages dplyr. So you have to do that. And so that you can have it installed, then you call it up in your library. No. Okay, so have we all successfully called up dplyr? dplyr is the package that we're going to use to merge week 0 data frame that we created with week 12. And the command that we're going to use is called the rbind. Rbind is row bind. Row bind, I think about it like, the way I remember it is, row bind is like stacking the rows one on top of the other, okay? Because there's also column bind, where you're just like adding more to the side to make it longer, so to make it wider. But row bind, just going to put column, you're going to put week 0 on top of week 12. Does it make sense what I'm saying? Hello, everyone. We actually need to move a bit faster. We have 17 minutes more. Hello, everyone. Can you hear me?
Yes, I can.
Okay. So I am going to run this chunk of code to stack week 0 data frame on top of week 12 data frame. So now it gives us one data frame that is now called weeks. And then we just come and do the test, the t-test, the paired t-test on the data, on the, what's it called? On the data that we just stacked called weeks. This is, so it's basically t.test hours, which is the number of hours they've worked till the week, paired is equal to true, and the data, the name of our data frame is weeks. So if you run this, you get exactly the same result. It's just that you did not use it's just a different way of running the same thing. Is it okay to move on?
Yes.
Okay, so I'm actually not going to run through example 3. I'm going to go to practice 2. So here we're going to, similar to the just following up on the calorie example that we had, calorie intake example that we had earlier. This time around, they actually collected information on calorie consumption on the eve of the Eid. The mean calorie consumption was 2,100, SD was 150. Then on the day of the Eid, they collected calorie consumption information on the same set of people. Mean was 1,850, standard deviation was 300. So now we have a paired t-test, right? Because we have before Eid and after Eid information for each participant, for each of the 100 people. So this is, okay, so I already put this here. So because we don't have the data set for each of these 100 people, I'm basically asking R to create a simulation data test. I call what happened on the eve of the Eid, I called it pre-Eid. And I say, create this normally distributed data set of 100 people. The mean calorie is 2,100, the standard deviation is 150. And then do the same for the day of the Eid. 100 people, normally distributed sample, mean is 1,850, standard deviation is 300. Then I say, I want the paired t-test. My X, or my first data set, is the pre-Eid data. My second data set is what happened on the day of the Eid. It is a paired t-test, and I want a two-sided test. Is this, can you please look at these 3 lines of code and tell me if it makes sense how we got here and what we're doing?
Yes.
Hello? Okay. Chialoka, you think it makes sense? Mamuda, Omotoe,
Yes.
what do you think?
Yes, it does.
Okay. Okay, so I'm just going to run that chunk of code, and here is my result. R tells me it's a paired t-test. What do you guys think? Anybody? Anybody want to take a shot at interpreting this?
The result is statistically significant, and it
Okay.
shows the mean difference lies between 197 to 319, and because of that, we can say the mean, the pre-Eid, the consumption, calorie consumption pre-Eid is statistically different. Pre-Eid and post-Eid are statistically different.
Okay, thank you. Thank you. I agree with your interpretation. Is there any question around this? Okay, I'll take that as a no. So I'm just going to go ahead and talk about the independent sample t-test. And this is t-test when you have 2 groups that are independent. There's no relationship, like they're not the same people. And this is a lot of what we see in, like in real life, in biomedical and social sciences. You get a group of people, you put them in 2 or more groups, and then one group gets an exposure, maybe another group gets a different exposure, and then you want to see if there's a difference in their outcomes. And the example that we have here is a clinical trial that randomly assigned 1,500 pregnant women to daily iron supplementation or placebo. And they want to find out whether the iron supplementation increases their hemoglobin at the time of delivery. Of this 1,500, only 982 women were identified at the time of delivery. So now we have the hemoglobin data. Data on hemoglobin concentration at the time of delivery, and we want to compare the average hemoglobin in those who received iron versus those who received placebo. So remember, these are 2 independent groups. What happened to one woman has no effect on what happened to the other woman. So independent t-test. We are going to import the data set. And this is the data set. It's the iontrial.csv. And because it is .csv, we're going to use the read_csv command. So can we please import our data? And let me know if there's any challenge with importing the data. If you've imported your data, then go ahead and look at what the data looks like. So use the add command to look at the first three observations. Use the table 1 command to look at the variable hemoglobin and just create a table around it. Create a table of the different values of a summary table of that variable called hemoglobin. That's what I would do here. Please let me know when you've done it, or let me know if there is a challenge. How many columns are in your table?
Three
I
columns.
have 3 columns.
Okay,
Column.
great. Okay, I have 3 columns too. Can we then go ahead and just summarize using the create table 1? So remember, you pull up the library table 1, then you specify the variable that you want to be summarizing. It's the HB, the hemoglobin variable. And then you say create table 1. You want it stratified by the treatment group. You specify the name of your data frame. It's iron trial. If you've run it, you can see how the table 1 package or the table 1 command has created the summary statistics, and it has stratified by the treatment arm. So you have treatment is 0, that's a placebo, and treatment is 1, that's the intervention group. And for each group, you can see the number of patients, the number and percentage of observations that are missing, the mean, standard deviation, all those things. And here we can also create a box plot. Remember how we created the first box plot? You specify the variable that you are that you want to that you want to chart, and how it should be stratified. This is the name of your data set. You want to specify the name of your x-axis, the label of your y-axis, and you can even put a line, like a trend line. So let's run that and see what it looks like. Please let me know if you're able to get this. Are we together?
Yes, we are together.
Okay, so now we're going to run the t-test using the same t.test command. And it's very similar to what we did with the paired t-test. So we specify this is my variable, HB, that's my outcome variable, TRT, that's the independent variable. And then here we just say paired equal false. So we're telling this is not a paired t-test, this is an independent t-test. And that is the difference. So if we run this, R will tell you, I ran a 2-sample t-test, a Welch's 2-sample t-test. It's different from what happened the last time when it was a paired t-test, right? So does anybody want to take a shot at telling us what this means?
I think it's just saying that it is not a paired t-test. They are independent tests.
Absolutely.
They are not paired. They are not the same population.
Great. What else do we see in this output? Yeah, what does it tell you?
It
There's
is
a difference in
significant.
mean.
This doesn't tell us the significance, actually. It says mean in group 0 and mean in group 1. So it's telling you group 0, which is the placebo group. This was the mean hemoglobin at delivery. And group 2, which is the treatment group, this was the mean hemoglobin at delivery. Because when you're writing, think about when you're writing your result or your report, you're not just going to say, we did a 2-sample t-test and it was significant. You have to tell people what you found. So we'll say the mean in the placebo group was 10.8. The mean in the treatment group was 11.7. The 95% confidence interval of the mean difference was minus 1.11 to minus 0.62, right? And then the p-value is 4.73, negative, all of that. So it's less than 0.001. Let's not just rush to the p-value, because the p-value doesn't really tell much. It can tell us, yes, significant or not significant, but as people who want to implement interventions, sometimes you want to see the size of that difference. It's not just a p-value. We have to, slow down a bit and report the mean in the different groups, the mean difference, all the other things that go with the test. So is this clear? We have 3 minutes. It's unlikely that we're able to go over the ANOVA part of it, but I just want to, is this clear? Are there questions?
Yes, it is clear.
Okay, I'm going to put my email address in the chat. So if you have questions, you can send me an email. And so here, I'm just going to almost like review the ANOVA and say the ANOVA is when we want to compare mean across 3 or more groups. The t-test, 2-sample paired t-test, they are for mean in 2 groups, mean differences between 2 groups. So once you start going beyond 2, 3, 4, and above, you want to use the ANOVA. And there are assumptions that are required before you use the ANOVA test. And one that we can quickly look at, the fact that the data is normally distributed or the sample size is large, that's a characteristic of your data. You can tell that by looking at the number of observations. The assumption that the samples are drawn independently, it's a characteristic of your data. So you are the one that would look at the data collection plan and determine that, okay, these are independent samples. The statistical test is deciding that the standard deviations are approximately equal. And basically, you can just use table 1. The table 1, The table 1 command that we've used before. If you use that, you'll be able to see the standard deviations for the 2 groups, and then you'll be able to decide whether they are approximately equal or not. And then implementing the ANOVA is just this command where you say one-way ANOVA. This is just the name of the file, and then the AOV, you specify your outcome. What is it that you're looking for? What's the dependent variable? And then you specify your independent variable, which is what treatment they received, and then the name of your data file, and then you run it.
Excuse me, please, in that line 387, after SBP, systolic blood pressure, this icon, I do not understand. Is it ash?
No,
ash?
it's tilde. I don't know what, I use an HP, and on my HP, it is